Okay guys, so this is a session about buffers, and throughout this video I'm going to be stopping every now and again to ask a question. When I do, if you can pause the video and on a whiteboard or some scrap paper, if you could try and write the answer down, then press play again, and then I'll go through the answer and it'll just let you know whether you're on the ball with stuff or whether your ideas are the right ideas and where you're going wrong. So the first question I'm going to go through is, what is a buffer made from? So I'm going to take you part of the way and then I'll start asking some questions. So a buffer is a combination of a large, what we call a large reservoir, a large amount of weak acid, and it has to be weak. We'll talk more about that later. So if ever you're asked this, that word weak is necessary, which I'm going to represent with HA, where H is the proton the acid donates and A is the rest, and a conjugate base of that weak acid. So in a second, stop the video and try and answer the question, what is a conjugate base? Welcome back. And so a conjugate base is the acid when the acid has donated the H+. So if this is the acid, the conjugate base would be A-. And we can link our weak acid and conjugate base in an equilibria with just the H+ next to it. So there's two ways of making a buffer. If you think you know what those two ways are, stop the video now, try and scribble them down. If you've got literally no clue, just carry on. Bonjour, welcome back. So two ways, there's the main way, the normal way, and then there's what I call the sneaky way. So we'll go through the main way first. What we want is a large reservoir of weak acid and conjugate base. If we have that, we have a buffer. So how can we do that? Well, method one, we simply add a large amount of acid. So let's, rather than using A- and HA, let's apply this to an actual equilibrium now. Let's use ethanoic acid. So CH3COH. Conjugate base, because it's lost that proton, that H+, and look, there it is. So the first way we can do is by simply adding a large amount of weak acid. Now, when I add a large amount of weak acid, it's going to give us loads of this. So if the bar represents the amount we have, and then also, because weak acids partially dissociate, hence the reversible sign, we're going to get a little bit of conjugate base and a little bit of H+, but practically nothing. And obviously the weaker the acid, the less we'll get. So as well as this, we also need to add a salt of the weak acid. So a sodium salt would be fine. You could use a magnesium salt, but just have a think about this one. You don't have to stop the video. Why might using a magnesium salt be a little bit of an awkward thing to do? Well, the answer is because magnesium's 2+, so you need to balance it with two of them, and it just becomes a bit more complicated. So it's fine to do that, but I would just use this. Now, salts, providing they're soluble salts, and sodium ones are, will fully dissociate in an aqueous solution. So when you add your salt, you're not actually getting a salt. What you're getting is a little bit of metal, which we don't care about, and because it's fully dissociating, a large amount of this. Well, what is this? This is the conjugate base. So we add the weak acid to get a large reservoir of weak acid, and we add a salt so that it fully dissociates to give us our large reservoir of conjugate base. So at the end of the day, we've got a weak acid and conjugate base, we have a buffer. There is a second method though, which is the sneaky method. So method number 2. Let's say I add, let me just reset this. Let's say I add a large amount of weak acid, we'll use the same one. And let's say I add 10 moles of this. I now have a large amount of weak acid, and a little bit of that, and a little bit of that, for the same reason as before. What we can then do, and the reason this is sneaky, is nobody ever realised this produces a buffer. It's hard to kind of spot it, so really watch out for this if it's anything to do with buffers or acids in general. Let's say I added a base, let's say a strong base like sodium hydroxide. They're going to react. If you could stop the video in a second, stop the video, try and balance that equation, and then try and write down why is it that we're going to end up with a buffer solution. Okay, welcome back. So what we're going to do is we're going to get our sodium ethanoate and our H2O. But let's say I've only added, 5 moles of sodium hydroxide. What's that going to do? Well, it's going to react with 5 moles of my ethanoic acid to leave 5 moles. And as it's a 1-to-1 ratio, we're going to produce 5 moles of our salt. But think back to before. What is the salt going to instantly do? Well, it's going to fully dissociate. So what happens is some of your weak acid, so this goes down a little bit, but we've still got lots, is being changed into salt, which gives us our large reservoir of conjugate base. Now it's really important to note, this only happens if your weak acid is in excess. Look, we had more moles of weak acid. If I added the same amount of each, or if I had an excess of sodium hydroxide, it's going to use up all of your weak acid. We'll get loads of conjugate base, that'll be fine, this will be massive, but we'll have no weak acid, so we will not have a buffer. So that's the 2 ways of making a buffer. The big question which you're going to want to know about is, how does a buffer work? So if you think you know this one, stop the video, try and write down, and you can just use the general term HA goes to that. How does a buffer minimize a change in pH, because that's what buffers do, when we add a small amount of acid and base? Okay. And welcome back. Here's how we do it. So this is what I call like a skeleton answer. So I'm using like general equations. After this, we'll go for another specific one, which I'll set as a question. If I add an acid, what am I really adding to the solution? Well, we're adding H+, aren't we? So what if I add an acid, what's going to happen is the concentration of H+ will increase. Concentration of H+ increases. Well, think about Le Chatelier's principle, dynamic equilibrium from last year. What's going to happen then to the position of equilibrium? Well, if we increase the conc of H+, the position of equilibrium will shift to the left. H+ increases. Now, I'm going to be lazy and say POE. Don't ever do that in the exam, don't abbreviate. POE shifts left. And this is really important. We've got to actually show what reaction that represents. Well, if the position shifts to the left, then H+ and A- one way, because we're getting one way now, is going to HA. You've just got yourself the mark, sometimes 1 or 2 marks. So how does this work? Basically, if you add an acid, the conjugate base soaks it up. And so all the extra H+ you're adding doesn't stay in the solution, it ends up getting transformed into HA. And so there's no extra H+, or very little extra. Remember, it minimises changes, doesn't completely stop them. And then we've got the alkali. So if you didn't try this question before, because you just didn't have a clue, hopefully you've got a bit of a clue how it works now. Maybe you could stop the video and try and do it for alkali. Welcome back. So with an alkali, what we're adding is OH-. What's that going to react with? Well, it's going to react with the H+ to make water. And so what are we doing? We are using up the H+, so we're going to decrease the concentration. H+ concentration decreases. What's that going to do to the position of equilibrium? Well, that's going to shift the position of equilibrium to the right. So position of equilibrium Remember, don't abbreviate in the exam, shifts to the right. And let's give an equation to show that. So that's going to be HA goes to A minus NH plus. Okay? So this is kind of like the model answer. And literally don't say anything else but this if you're explaining how a buffer works. All you need to do, literally all you need to do is, based on whatever actual equilibrium they give you, substitute the HA and the A minus for the actual chemicals in the question. And then we're done. That is literally all you need to do. So I'll pop up another example for you to have a go at. Okay. So let's imagine I've got this buffer system. I've got phenol. And that is dissociating to make a phenoxide ion. Can you explain, and this would be between 3 and 5 marks depending on how they're feeling, can you explain how does this buffer system minimize a change in pH when we add a small amount of acid or base? So stop the video. Buona stente, welcome back. So with an acid, and you'll notice it's just the same answer as what I just did. I'm literally just swapping this for the HA and this for the A minus. But just to show you that the conc of H plus increases, so the position of equilibrium, so conc increases, position shifts to the left. So what equation are we going to get? Our phenoxide and H plus goes to phenol. That's almost a hexagon. How about if I had an alkali? Well, an alkali releases OH minus, which will react with the H plus to give water. So I have now decreased my conc of H plus. Position of equilibrium will shift to the right. Conc of H plus decreases. Position of equilibrium shifts to the right. And we'll just show an equation to show that. So phenol is going to go to phenoxide plus H plus. What's actually happening? Usually your OH minus soaks up the H plus, increasing the pH. If you've got a buffer, as soon as your alkali soaks up the H plus, the weak acid dissociates to replace it. And this is why it has to be a weak acid. If it was a strong acid, it would just dissociate all of them anyway, and so you wouldn't get this effect. You would also have no reservoir of acid, because it would all fully dissociate. So that's why it has to be weak. So that's buffers.